Hello everyone. So today we're going to be going over the momentum heat mass transfer analogy from the perspective that the flux, momentum, heat, and mass are related to the respective gradients, the diffusivity that has units of meters squared over seconds. So all these are related to each other. So our heat is high temp going to low temp. Mass going to high concentration to low concentration. Our momentum from the high flow to low flow. So this can all kind of be summed up the concept of diffusivity, which is the measurement of how much something is going across something in an amount of time, or area over time, which can have the units of meters squared per second. So looking into each respective analogy, first we'll be going over heat. Actually, we'll go over momentum first. So inside momentum, we'll be going over Newtonian fluid with our shear stress is equal to our viscosity and then our velocity gradient with respect to position. Make that a dy. So to get this one, we're going to divide and multiply by our density. So on our velocity, we'll add a density, and then our viscosity will divide by density to make sure it equals 1. So in this, our units, since the density is on the bottom, meters cubed over kilograms, and then on the top, we have kilograms over meters seconds. So these kilograms will cancel out, this meter will cancel out, giving us meters cubed per second, or our kinematic viscosity. So our next term, we're going to be going over heat. Which we'll be using our energy equation. So Q equals temperature gradient, or not our temperature gradient, our thermal conductivity, and then our temperature gradient with respect to position. So here we're going to be multiplying and dividing by our our heat capacity and our density. So our thermal conductivity so the following. So we're going to be paying attention to this value right here, where we can first go over the density, and then we have our thermal conductivity, which is joules, meters, kelvins, seconds, and then our heat capacity, kelvins, kilograms. So this will then get us joules, the square root of our kelvins, our kilograms, and get rid of 1 meter, giving us meters squared per second. desired units. So we can keep that in mind going forward. Our thermal conductivity divided by our heat capacity and our density is equal to thermal conductivity, or thermal diffusivity, excuse me, or this alpha, which has units of meters squared per second. For our last one, we're going to be going over mass, which we'll kind of be using like an arbitrary kind of thing. So for mass, we can denote this by J, E, and our concentration derivative with respect to dx. And so for this one, we're going to divide by density again. So we'll actually be dividing by density. Sorry, excuse me. Dividing by density, sorry. So this meter square will cancel out. This kilogram will cancel out, giving us meters squared per second, or our concentration diffusivity. So all of these are connected by their diffusivities, making them all related to each other. Thank you very much. Hello everyone, so today we're going to be explaining Fourier's law, the units for flux, thermal conductivity, and temperature gradient. And why is there a negative sign? And then additionally, we're going to explain the difference between thermal conductivity and thermal diffusivity. So to start, we're going to focus on Fourier's law. Which is an equation that represents heat flow via conductivity. And this equation relates the heat flux to the thermal conductivity, negative thermal conductivity, and then to the negative temperature gradient with respect to position. So this is represented by Q, negative K, dt dx. So to kind of look at some of these units, we're going to kind of go with them step by step, first attacking the temperature gradient. So temperature gradient is pretty self-explanatory, as we have kelvins over meters with the temperature and the position over here. And then the next one we're going to go over is our thermal conductivity, which is equal to joules, meters, kelvins, seconds. So then, to try to get our heat flux, we can add these two up, or I guess multiply them together, where we have kelvins over meters, and joules, meters, kelvins, seconds. We can get rid of these kelvins. Here we get joules, meters per second squared. So this kind of leads me back into that's a heat flux. And we have our meters seconds. So flux is area, time. So this would directly contribute to this, as this is our heat flux, so it measures energy, and then we have our flux with the meter squared times seconds, which is represented by the area times the time. So you may be asking yourselves, why is there a negative right here? Make that equal. So The negative exists because temperature goes from high to low. It looks for the lower energy area and attacks that. So in essence, temperature or heat is going from high to low or in the negative direction. So the main difference in our last topic is the difference between thermal conductivity versus thermal diffusivity. Or K versus our alpha. Alpha being represented by thermal diffusivity, K being represented by thermal conductivity. So it's really pretty easy. So our alpha or thermal diffusivity is simply just thermal conductivity over our heat capacity and density. So you may be asking, well, this kind of seems very proportional to each other. What's really the main difference? So I'm going to give an example here. So let's say we have two bars, both made, have the same thermal conductivity, and they're like half submerged in a very hot area. All equal to each other. So that dotted line represents hot side and cold side. Except for bar 1 has much higher density and heat capacity. The other one, with bar 2, has a very low density and heat capacity. So looking at this, the temperature would actually go, diffusivity would go much slower on bar 1, whereas opposed to bar 2, very fast. It goes much quicker traveling down the bar to the colder side. So that kind of sums it up. Even if they have the same thermal conductivity, they can actually, the heat flux will be very different depending on that density and the heat capacity of both respective properties.